All right. So now I'll be talking about simulation. That's actually the main work that I do at Waabi is mainly on sensor simulation. So I'll try to give an overview about the recent developments that we've had the past couple of years. There's been a lot of work recently, especially in data-driven simulation for self-driving. And so I'll give a quick overview of why we need simulation, some of the recent work, and what you would want in a closed loop sensor simulation system, and remaining open directions. Cool. So as you can see here, deploying self-driving vehicles in the real world is quite challenging, especially if you do most of your development and deployment strictly in the real world. And you can see here lots of different things that might happen. For example, elephants or a bear. And this is really the long tail that makes it difficult to get self-driving vehicles to work in a robust and scalable manner and a safe way. And it's not really feasible for us to just take an autonomy system, put it on a self-driving vehicle, and then just drive millions and millions of miles, hoping that we'll encounter some of these situations, and only then to know that we don't perform well in those situations. So we need a better way to be able to expose the system to all these situations, provide them as learning data for these type of data-driven autonomy models, and then test and make sure that we can actually handle these situations in a robust and safe way. And so this workshop or this tutorial on simulation is going to be talking about kind of the current ways we do simulation in the industry that are like somewhat standard, and why they don't really meet the goals that we want in a closed loop simulation system for evaluating autonomy. So maybe not sure how familiar people are with these types of simulation, but I'll quickly go over them. First, there's log replay simulation. So this is where you have a self-driving vehicle, it's driving in the real world, it collects sensor data, which is LiDAR and camera, and it stores it into a log. And then you can take that data and then play it back to the autonomy system. The autonomy system can run that data and then generate outputs. So this is kind of like watching a movie. You're just absorbing the data, outputting it. But then autonomy outputs such as like motion plans can't actually be executed by the autonomy system because you already capture the data. So it's only log replay. This is called open loop evaluation. There's also a couple of papers this year at CVPR that talk about how open loop evaluation is not very sufficient for testing the full system of your autonomy system. So full performance of your autonomy system, sorry. So there's limitations with log replay. And also you still have the same problem that I talked about in the earlier slide where you have to collect data, like millions and millions of miles to get all these scenarios in the first place. So the other approach that is available is called motion planning simulation. This is where you can generate the agent behaviors in simulation and then send the bounding boxes and trajectories as ground truth perception and prediction outputs to a motion planning module. So this assumes that your motion planning system or your autonomy system is modular, that you have a standalone motion planner. And then you can send these autonomy outputs to that planner and then see what it does in closed loop, because you can then actuate on it and then put the PMP outputs that you generate into a new coordinate frame based on where the STV is. So this allows for closed loop evaluation. But the challenge here is that we are not actually running perception and prediction. There's no sensor data being simulated. So you can't actually test the full system performance, because a lot of the challenges with autonomy is actually that the future of the real world is multimodal. There's lots of different possibilities, and you actually have to send that to the planner for it to actually like negotiate around those different futures. Then the last type of simulation that's standard in industry that is not that common, but is used in certain situations is data generation. So this is where you have a game engine like synthetic environment, potentially through procedural content generation and artist created assets. You can put these assets into a particular scene, and for like rare objects such as say fire trucks or ambulances that you don't see too often day to day, you can generate lots of synthetic data that you can then augment your perception data sets for. So you can use this in a small amount to kind of improve your perception models for certain cases, but you can't actually use it very well for full system end-to-end testing on particular scenarios. And the reason why is because there's a domain gap. You often can't get the performance of your autonomous system to be realistic in this type of virtual world compared to the real world. So those are the standard types of simulation that are used in industry, but it doesn't really tell us for a particular scenario, what is the performance of the autonomous system in simulation, and does it actually show what it would be like in the real world? So I'll now talk about like what type of attributes we might want in a self-driving simulation system. And then in the second half of this like tutorial, I'll be talking about them specifically with respect to sensor simulation, digital cloning, and asset creation. So the first type of attribute we want for a self-driving simulator is we want it to have diversity. We want to be able to capture all the different things we see that exist in the real world. A second aspect is speed. We want to be able to run simulation on millions and millions of scenarios because there's so many things that can happen. We want controllability to be able to specify any type of scenario we want that we might encounter in the real world. And of course, realism. So this is about being able to be indicative of performance of what you might see in the real world. And immersiveness. So this is where, compared to say NP-only simulation, where you only simulate the actor trajectories, we want to simulate the sensor data as well. And then we want it to be reactive, which is the closed-loop evaluation setting. The SDV should make a maneuver, the other actors should react to it and react to each other. And another important part of simulation is it should be able to provide feedback about the autonomous system's performance. This is about saying computing collision metrics or safety metrics and comfort, so that we know that the autonomous system is improving and also that we can see where it's failing. And then we want it to be scalable, which means being able to run this at not too much expense. I already talked about the other methods that are available through simulation, such as log, replay, motion planning only, and synthetic data. So log replay simulation, you primarily can only do open loop evaluation. Motion planning only mode, you can do closed loop evaluation, but you can't simulate the sensor data. And then there's synthetic data generation, which is using those procedural environments to generate sensor data, but it's not very effective for doing full system closed loop testing. All right, and then I'll add one other additional line here of recent works that are called like world models. They take advantage of recent techniques in generative AI, such as diffusion models and transformers, to try to learn on large corpuses of video data as well as text data, and implicitly learn the physics of the real world into these generative world models. And they also encode implicitly the appearance. They've been able to generate very realistic and diverse videos for self-driving scenes, but they still have several limitations that make them not suitable for full closed loop evaluation. So the first aspect is they're kind of still slow. For example, stable video diffusion takes a couple minutes to generate several seconds of self-driving simulation video. They're not that controllable. You can provide coarse text queries about a particular scene you might want, but you're not able to control the exact location of different actors, the time to collision of those actors with the self-driving vehicle. And you may want that type of flexibility and fine-grained control to know the exact performance of your self-driving vehicle. Additionally, they're not that immersive and they have like reduced reactivity. So there's been recent work on providing like action conditioning to these world models, but it's not clear like how high fidelity this is. You can imagine, for instance, a very high dense traffic scenario. The SDV accelerates into it, and sometimes these world models will just make those actors disappear to make it more suitable to what it's seen in the data distribution. And additionally, these type of world models, because they implicitly encode the physics, it's hard to compute like exact metrics of have I collided with an object or not, or am I having a comfortable maneuver with respect to the other actors in the scene. And of course, these are somewhat expensive to train currently. So the goal that we're trying to do at Waabi is to build a simulation system that tries to achieve many of these attributes. And the way we try to do it is that we want to be able to build a simulation system that is explicitly grounded in our physics and has actual 3D representations. So you can kind of think of this as the way you play like a video game, say like Grand Theft Auto, but instead we want it to be data driven in every aspect of our simulation system, specifically for autonomy evaluation. So we can still use generative AI techniques to be able to create very highly realistic assets and content and also behavior models, but we can also still use computer graphics to make them fast and controllable, to use machine learning to make the actors intelligent and reactive and provide learning-based feedback and et cetera. And also by taking this kind of modular approach, we can achieve a bit more scale and at lower costs. So I'll quickly walk through like what a closed-loop simulation system looks like. So first, there's a simulation specification. This is where you specify all the actors in the scene, as well as the goal of the scenario that you want to achieve. And in addition, you might also specify the environment conditions of the scenario. So what the weather is looking like, the sensors that you want to simulate for your particular scenario. That goes and initializes a world state. And then from that world state, you can load in the assets that are required to represent that scene, such as the dynamic actor vehicles, the background, pedestrians, etc. And then you can simulate the sensor data according to the vehicle platform that you are interested in evaluating. Once you have the sensor data, you can feed that into your autonomy system, and it will generate outputs such as, say, steering and acceleration, for example. And then you can give those outputs then to a vehicle dynamics model, and the dynamics model then updates the state of the self-driving vehicle, its new location, velocity, acceleration, etc. And additionally, you can update the other actors in the scene based on the STV's behavior as well as each other's behaviors. And this all goes and updates the world state. And then this is a closed loop simulation. You can unroll the scenario out. Another aspect of simulation that's not often talked about is latency. So, for example, in a particular truck compute or vehicle compute, it takes time for the autonomy system to take the sensor data and generate actuations. And this type of delay is very key to measure and model in order to have strong bounds on the reaction performance of your self-driving vehicle. And oftentimes you're running your simulation system in a software in the loop setting. So you're running your simulation and self-driving autonomy system on cloud compute, which is not indicative of the actual hardware compute you run on your autonomy system on the actual self-driving vehicle. So you need to then model and estimate how long it takes to run different modules of your autonomy system and how long it actually takes to generate those final actuation outputs. And that's a key part of latency simulation. And then the last component is an evaluator, which says, I will take the world state at each time step and see how the autonomy system is doing, and then provide feedback to it. You can also use this evaluator to provide an assessment of how well the self-driving system is doing on a set of scenarios, and then understand which situations it's not doing well and which ones it is. So those are all the aspects to a simulation system. And here's kind of a streamlined format of it. And this is next couple of slides are just to show that if you have the framework of a full closed loop evaluation system, you can do a lot of the simulation modes that we talked about in the previous slides. So for example, here, this is the same diagram, but now we replace the sensor simulation model and the behavior models with the original data from the log. And at each time step, you can replay the sensor data and the actor trajectories that you have from that sensors into the autonomy system and see how it performs, and then run the same evaluation system. Here's another mode that we talked about, which is motion planner closed loop simulation. So here, instead of having sensor simulation, you can replace it with a realistic perception prediction output system. So you can kind of learn, there's like a paper that we had in the past that showed that you can learn what are the types of errors that perception and prediction systems make. And based on that, train a network to generate that given a particular ground truth scene configuration. And you can give that then to the motion planner to then see how it will perform in this type of closed loop framework than just providing the ground truth actor trajectories initially. And then there's synthetic data generation as well. All right. And then the other aspect of the simulation system is that there's a variety of ways you can initialize the scene, such as log-based or heuristic initialization or procedural generation, or even specified exactly by a human. And then you also have a wide variety of ways of specifying the behavior models that are controlling all the agents in the scene. You might have a high-level orchestrator that controls all of them together. You might have heuristic actor models or even data-driven models that are trained to kind of mimic a particular behavior of a driver or agent in the scene. And given the wide variety of models you have for scene initialization and actors you can do different types of applications of testing for simulation. For example, adversarial actors, or to be able to test, say, coverage, to making sure you cover all the different scenarios you might want to handle for simulation. Cool. And then rest of this tutorial, I'll probably primarily be talking about sensor simulation and asset reconstruction, as well as hardware, like the full system simulation system. And after this session of simulation, there's a talk by Kelvin. We'll go over into more detail about how you initialize the scene and how you actually model the behaviors of all the actors in the scene. So yeah, in this year for the tutorial, we split the sections up a bit differently. I'll be talking primarily about virtual world creation, so building the assets, simulating the sensor data, as well as the vehicle platform modeling. So I'll talk at a very high level about the vehicle dynamics model that takes in the actuation outputs from the SDV, as well as hardware in the loop simulation at a very high level about the latency modeling aspect of simulation. And then the second session, we'll be talking about the scenario representation, as well as agent dynamics. All right, so we'll now talk about virtual world creation. So here's a quick recap. I mean, I already talked about it earlier when we discussed all the different attributes you might want in a simulation system. It's even more so the case when you're trying to build a virtual world that you want to simulate highly realistic sensor data for. You want to have realistic assets, controllable assets, so being able to change, say, illumination conditions or the shape of your actors. You want to have a wide variety of actor shapes and classes, and you want it to be fast to render with. And yeah, in the past, a lot of ways that people have built assets are with CAD models. And this often requires manual creation by artists. And this can be quite expensive and slow. You can have very high controllability, but in order to achieve very high realism, you often need to have a lot of manual effort to do so. And so one way we can overcome this is to instead use the self-driving data that we've collected in the real world and use it to build our assets instead. So this is called like digital twin cloning or reconstruction. We can leverage a lot of the recent techniques from, say, neural rendering to reconstruct the assets from sensor data and then leverage those assets in simulation. Cool. And so we'll now talk about the different aspects of asset reconstruction or digital twin cloning in the next part of this tutorial. So there are three ways we kind of separate the asset categories in together, but there's also recent methods that kind of combine all of them all in one place. But there's background assets, which is kind of like the static scene elements you have in the scene. There are rigid actor assets, such as your standard vehicles. And also there are deformable actor assets, which are like pedestrians, in some cases like motorcycles or cyclists, that you need to model the motion and the deformation of the meshes themselves. So now we'll talk about background asset creation. There's different ways you can reconstruct the assets. A lot of the work these days is on neural rendering, but I'll quickly go over some of the classical methods that have been used in the past. So of course you can aggregate like LiDAR data or do, say, structure for motion to create an initial geometry of your scene. This is pretty simple, scalable. It's very standard way to do it. But there can be noise when you aggregate the LiDAR together. There can be holes in your meshes, especially in like, say, structure for motion and CoMap. You're not able to get, unless you have a lot of views of the scene, a very high quality mesh. All right, and then there's these recent works that are based on like neural rendering and per scene optimization. So given a sequence of sensor data, you can reconstruct the geometry of the scene by just by remodeling the sensor rays. So this is where actually a lot of the work that you're doing for asset reconstruction can also be reused when you're actually running sensor simulation for rendering to actually simulate the sensor data itself. Because these techniques apply the idea of, if I can recreate the sensor data, I can reconstruct the scene. So here we can see a neural rendering representation that's reconstructing the mesh for the collected sensor data. And it's pretty realistic, but the challenge is that you can only reconstruct the areas you observe, so there's no scene completion, and you're optimizing per scene. And currently, sometimes the neural rendering techniques can be quite expensive to train. But as we'll see in future slides, there's been a lot of progress in the community, such as with Gaussian splatting, that accelerates the training time it takes to build these scene representations. All right, and then there's also the idea that instead of training at each individual scene, the sensor data to reconstruct the mesh and assets, you can try to learn a generalizable model. So this trains on multiple scenes all together jointly. So for example, NKSR has learnable kernels that learn across large ground truth synthetic scenes to convert unstructured point cloud data to local meshes. And it achieves pretty high quality and is also reasonably fast to run at inference time. And there's other recent methods too that kind of like take in very sparse sensor data, such as a small collection of images, then tries to output a pretty dense reconstructed scene. But it's typically working on kind of more smaller locations rather than on large scale scenes. And yeah, there some of the cons not doesn't apply for all of the methods here, but some of them can be quite expensive to train because you're training on large amounts of data. This can be like on the same order of say diffusion models, or that train on like large amounts of image data. And the prediction results are not going to be guaranteed to be faithful to the original ground truth compared to optimization methods, which are specifically optimizing for the reconstruction loss with respect to the original sensor data. And in some methods, not NKSR, for example, but you might require accurate normal estimation to get higher quality geometry. So that's on the background asset side. I'll now talk a bit more about the rigid actor assets. A lot of the methods still apply, but a lot of methods are out there that focus on these foreground actors in particular. Again, there's the aggregation-based approach, which achieves reasonable quality, but most of these papers are now kind of older methods of reconstructing the meshes compared to the most recent techniques. And then, of course, there's explicit mesh-based inverse rendering approaches. So here you have a template mesh, and then you try to optimize that template mesh with respect to your sensor data in like a differentiable rendering manner, and then predict the kind of shape. But you have priors now on basically what the final shape should look like. So then when you optimize with respect to the sensor data, you still have like a pretty complete asset. This is pretty simple and scalable, but it only works if your template is a very good initialization in the first place. Otherwise, the optimization can typically fail when you're trying to reconstruct particular actors in the scene. All right, and that's on the explicit-based approach, but there's also recent neural implicit approaches, such as like occupancy fields or implicit sign distance function fields that you can optimize with neural rendering techniques, similar to what we talked about for the background assets, such as like urban radiance fields. There are specific works that focus on foreground actors, such as vehicles or other rigid objects and signs and whatnot, and optimize the neural representation to reconstruct mesh. And then some of the works here focus primarily on like the geometry and the color, but there's also a very large range of works that focus on the idea of inverse rendering, which tries to decompose the asset into geometry, material, and appearance, and lighting conditions. All right, and then again, some approaches focus on like the idea of optimizing directly on your sensor data to reconstruct a particular asset. But just like in the background assets, you can train on large amounts of data and kind of learn a prior on the types of objects that you have. So here are like previous approaches that kind of train on multiple vehicles and then learn like a shape representation. And then kind of say, given a single image or a set of images, predict a pretty dense, high quality shape from it. But again, the same artifacts can appear when you have a prediction-based method compared to optimization. It may not fully match the original reconstruction you had in mind. And depending on how far away the objective is that you're trying to reconstruct, if it's out of distribution, you might fail. All right, and then yeah, there's now also quite a rich line of work on generative modeling to create these assets instead, but they're typically used more in the art field and kind of like synthetic assets that you think of when you look at some of these like visuals here. They're not fully used right now in trying to like build high quality real world assets for say self-driving simulation. But it's a very promising line of work too, where you can just provide a text query or a single image condition and generate a pretty highly complete asset. And yeah. And then the last type of foreground assets I will talk about before moving to deformable assets is adversarial actors. So there's a lot of work that says I can focus on reconstructing the real world, but I can also look into understanding from a purely simulation standpoint, what types of actors or assets cause problems to my autonomy system. And you can optimize the mesh if you have a differentiable rendering framework to see what type of meshes are causing the most challenge for your perception model, for instance. And there's also recent works that try to optimize nerf-based radiance fields to see what are the most challenging scenes in terms of geometry and appearance to your perception system. All right, and then the last aspect I'll talk about is deformable actor assets. So there's a first type of way you can reconstruct pedestrians and humans in your self-driving scenes is by having mesh templates. There's a long line of work such as with Simple, and now recently some works that do it for like animals such as horses that try to reconstruct your scene based on a single input image or sensor data and then using a template mesh that you can deform with some learnable parameters to estimate the deformed mesh or the posed mesh that matches the original observation. So these types of approaches are like quite robust in that you can always get a highly complete human shape, but it doesn't account for clothing and it doesn't fully match the original actors in the scene. And of course, there's now recent neural rendering techniques that build these types of pedestrian assets from sensor data. There's implicit volumetric fields, and there's also recent works that use Gaussian splatting, for instance, to model the humans mesh in conjunction. So there's like one paper at CVPR this year called Goem Avatar, which is pretty cool. You build a mesh of your like pedestrian, but then you apply Gaussians on top of these meshes to then do like higher quality photorealistic rendering. So that's on the asset side. I'll now talk a little bit about the sensor simulation aspect. Again, same desiderata of realism, controllability, diversity, and speed. There's many sensors available on a self-driving vehicle, but the ones of primary interest are LiDAR simulation, radar simulation, and camera simulation. So these are all light-based sensors, but LiDAR and radar are active sensors. You send a beam of light or wavelength light into the scene, see how the wave propagates with the surfaces it interacts with, and then receive the response curves to these waves. Then camera is more passive because you have many different light sources available in the visible wavelength spectrum. You have a sensor that then receives that sensor data and provides the response curves from the light sources available. So I'll now talk a little bit in LiDAR simulation. So here's a quick video of what a LiDAR sensor looks like. So we can see we can generate pretty high quality geometry. It's somewhat sparse in certain situations, such as above or below when we don't have enough density of the beams. But overall, for close by objects, you can get very high quality geometry. And the way LiDAR works is you send a beam of light, it hits an object, you measure how long it takes to come back to the sensor. That tells you how far away the object is. You can also see that the LiDAR is colored by intensity. So this tells you how strong of a peak of a response the LiDAR beam is to the particular object it hit. And that tells you some material properties of the scene as well. Okay, so there are many different ways you can simulate LiDAR sensors, and we use the same kind of Venn diagram last year as well. We just expanded the number of papers that are available to do this type of simulation because as you can imagine with the field growing very fast, there's a lot more papers these days that try to do sensor simulation for self-driving. And a lot of them are now recently combining the same three like fundamental aspects that you might want to build into a sensor simulation system. You have physics because there's a very exact way of how light interacts with the scene. You have data because you want to match a particular distribution of the noise that you see in the real world with your sensors. And then you have machine learning to kind of train on that data and leverage the physics to try to make a realistic sensor simulation system. Cool. So again, at a high level here, there's very different techniques available that you can use for physics, data, and machine learning. With physics, there's many different methods available in the computer graphics community for simulating light interacting with scenes, such as with ray tracing and rasterization. On the data side of things, you have a lot of data you can collect from the real world that might be useful for modeling sensor data. So for example, you can record how the LiDAR interacts with different types of materials and see at which point a particular object does not return LiDAR points from, for say, concrete versus say a highly reflective object. And then on the machine learning side, we have different types of approaches and architectures available to learn from real world data, the realistic sensor simulation. For example, there's generative models, style transfer approaches that take simulated data from a physics-based engine and converts it to more realistic real-world data. And there's also neural learning approaches that we talked about in the past for building the assets in the first place. So here, I'll quickly go over some of the past approaches that have been done to do LiDAR simulation. First is the game engine-based approach. Here, we're only using physics and we're only using artist created assets. So there's a bit of limitation, the realism compared to the real world data that you want to fit to. There's also more complex physics approaches. You can have very high fidelity physics models available for LiDAR sensors, but it just requires a lot more information about your scene that you could typically get from reconstruction alone. You have to have a lot of manual effort and high quality data collection to build very accurate material properties specifically for the LiDAR wavelength spectrum, and similarly for the geometry and illumination conditions in the scene. But with that, you can get pretty high quality LiDAR, but it's just a lot of effort and also not very fast at the moment. Then there's a lot of recent works on using real world data and then having a generative model predict from some type of lane code to simulate the LiDAR. So here you can see like you can use VAEs or diffusion models, and you can sometimes condition these models on particular input conditions, such as like an initial point cloud, but you don't have very strong controllability of the scene configuration. So it prevents it from being used fully in like closed loop simulation systems. And then, yeah, there's this recent work that has that most of the field is going towards, I feel, which is where you're trying to build assets of individual objects. And then you do like neural based rendering approach to kind of simulate the sensor data. So here, there's a couple of approaches that just build the meshes and do ray casting, and then apply ML at the end to add some noise to the sensor data to match the real world data. And then here, there's an example of like, again, an approach that's called like LiDAR DM that builds, that does additional aspects of the simulation system before doing sensor sim. So you can take a scene placement and then generate the meshes given the scene placement in a generative model style. But then you can then do standard traditional rendering techniques such as ray casting to generate the initial point cloud. So this is kind of a generative model combination with physics-based rendering approach plus some machine learning at the end to do the ray drop. And ray drop is where you send a beam of light of LiDAR and it will hit an object, but it may not come back to the sensor with enough signal to return as a point. And then there's a couple of works that are available for neural radiance field approaches that are specifically optimized for LiDAR sensors. So, for example, there's the neural LiDAR fields NFL that specifically tries to model an active sensor and accounts for some of the effects you might see with LiDAR data, such as beam divergence, multi-echo returns, such as like dual returns. If you send a beam of light, you might get two response peaks that you want to send back as points to the sensor. This is getting very high quality scene reconstruction, but it can still be slow to render. And it still doesn't take into the fact that you might need to simulate different types of sensor modalities. So I'll talk in the next couple of slides about recent works that do both camera and LiDAR simulation through neural rendering. Oh, I guess that's going to happen after I finish the camera simulation work. But I'll first talk about radar simulation. Radar is probably one of the most challenging sensors to do simulation for because it's so noisy. You are sending much larger waves of light into the scene, and there's a lot more noisy propagation effects that can happen with radar sensors compared to LiDAR or camera. And then based on these waves that you send out, you can get information that's not just about the appearance or geometry, but also the Doppler information, such as velocity of how fast different objects are moving in the scene. So overall, radars are much more challenging to simulate. But again, the same core components that you use to do rendering of, say, LiDAR sensors applies to radar, physics, data, and machine learning. Some methods try to like bypass the whole like rendering approach of radar simulation and try to generate directly the detections of the radar sensor, but it's still quite challenging and it's not yet been easily generated for large scale scenes with high fidelity. And the other challenge with radar sensors is that there's often a lot of black box post-processing to kind of generate the final detections. And there's a lot of physics involved that is about how the radar waves interact with each other and what's the best like peak to signal noise ratio, for example, of these sensor data to generate the final detections that you need to potentially model in your scene. So again, lots of different techniques, but still some challenges in getting highly realistic radar simulation data. And similar to how we have neural rendering for LiDAR and camera, there are several works that try to extend it to radar. But it's promising, but there's still focusing on maybe more small scale scenes, synthetic scenes, and yet not yet there's like a really scalable radar simulation approach that works on large scale self-driving scenes that are with lots of moving actors and with kind of the standard radar you think about, which is FMCW radar, where you get also the Doppler information. But yeah, lots of different neural rendering approaches available as well. And then the last sensor simulation I'll be talking about is camera simulation. So we're all very familiar with cameras, so I won't go into much detail about how cameras work, but they're very complicated. Some particular parts, such as the image signal processing pipeline. And as you can see here, from compared to last year's tutorial, there are a lot more works in camera simulation than ever before. It's crazy, right? There's 40 papers here. And a lot of them are in the neural rendering and Gaussian splatting and diffusion model type work that's been happening in the recent year or so. That's leveraging a lot of data and machine learning together to kind of generate pretty high quality camera data. So again, lots of work done in the graphics industry before because of video games to simulate camera data with high quality. But oftentimes you just need a lot of manual effort to build high quality assets for camera simulation. There's also recent, like previous techniques that build on like very just quick and fast view warping. So given some coarse geometry of the scene, I can warp my sensor data to new viewpoints for closed loop simulation. These work still like reasonably well and are fast. They just can't do all the different things you might want for sensor simulation, which is having fine-grained control of the actors and being able to have the SCV in a very wide variety of locations compared to the original trajectory. And then there's also the neural rendering approaches that we'll be talking about in more detail. So I'll quickly go over the previous work that's done in the past on the subtasks, but most of the work these days is focusing on full camera simulation. But in the past, there were works that tried to do certain aspects of camera sim. For example, some works focus on just the novel synthesis aspect of simulation. So novel synthesis is where we can take the original static scene and then render it from a new view. And then other focused on dynamic actor simulation, which is given the same scene viewpoint, moving the dynamic actors around. So this one focuses more on the static scene warping and novel synthesis, which is called Vista. It is image warping based on some estimated depth of the image. You can warp it to new locations of the STV. And then here's some additional works that have been focusing on the novel synthesis side. Some of them are quite like a bit old now, like Block Nerf, but there's also some recent works such as Innovis and Neuras that do pretty high quality novel synthesis through neural rendering and scene reconstruction. But this focuses primarily on the static scene, and there's also the dynamic actors to consider. And so there's one actual additional component for static scene novel synthesis, which is also scene editing. So it's not just about reconstructing the original scene, but being able to create new environment conditions that are totally unseen for that particular scenario. So there's work such as Climate Nerf that tries to create new weather conditions such as flood or snow, which there's lots of traditional physics-based rendering approaches available. It just can be either slow or you can only model it typically for, say, the camera sensor. You need to also do an additional modeling work for, say, LiDAR or radar data. And then there's also scene relighting, where given the initial geometry mesh, you can change the illumination condition and then run that through a physics-based render plus some machine learning to kind of generate new scene relighting. For dynamic actors, main challenge is being able to estimate the illumination conditions of your scene and then render those actors into new scene locations. So if you have good sensors such as fisheye cameras, you can capture pretty high quality environment maps for then putting into physics-based rendering engines. There's also some recent work called GeoSim, it's a couple of years ago actually, that does view warping-based methods for dynamic actor simulation. So given a dynamic actor mesh and a geometry texture that you project from a particular image, you can warp it to new locations. And now that's kind of talking about the subcomponents for camera sim. I'll now talk about the full system camera simulation approaches. So there's game engine-based approaches such as, say, Carla, or Grand Theft Auto as game engine-based approaches for camera simulation. You have full scene controllability, but the downside is the domain gap because there's a bit of a gap between simulated sensor data and real data, especially if you're trying to run your sensor simulation fast. Then there's the purely generative model approaches. So given some type of initial conditions, such as a segmentation mask, you try to in-paint the entire scene. This has some realism artifacts. And there's also the idea of using computer graphics plus image translation techniques to leverage both physics-based rendering and machine learning to generate more realistic camera data. Cool. And then lots of different works on neural rendering approaches. So you can simulate both camera and LiDAR through these type of volumetric representations. And there's also some recent works on Gaussian splatting as well that try to represent the scene as a sparse set of points that you can then just rasterize into the camera image to generate the rendered data. So pretty realistic. And with the Gaussian splatting, there's more higher frame rate, but can still kind of be slow to train. And especially for like Gaussian splatting and other neural scene representations, you can only really simulate viewpoints that are close to the original trajectory. There's still quite a bit of challenge and extrapolation from very far away viewpoints. And yeah, here are some recent works that are on the Gaussian splatting side compared to the neural radiance field work. A lot of recent works for Gaussian splatting for self-driving scenes typically leverage LiDAR data as initialization because typically Gaussian splatting doesn't have very high quality geometry. So if you can initialize from a geometry scaffold, you can then fit pretty well the Gaussians to the camera data that you observe. But yeah, there's a challenge with the limited viewpoints for kind of closed loop evaluation. And then there's some recent works. I think I kind of talked about this when I talked about editable neural radiance fields, but this is inverse rendering. So you can change the lighting conditions and use a combination of both physics-based rendering as well as machine learning. Yeah, and then here are recent works that do both camera and LiDAR simulation with neural rendering fields. URAD and Alignment are actually at this year's CVPR, and they kind of build off of the idea of leveraging both camera and LiDAR data to build higher quality scene representations. And by learning with both multiple sensor modalities, you can typically get better scene. And now I'll talk a bit more now into the kind of world model approach. One of the original works that tried to learn dynamics with the appearance is DriveGAN. And you can see here that you can have a lane code that updates the state of the world. And then you generate the camera data accordingly based on that scene configuration from the lane code that you have. But now there's a lot more work that's in this area where you train on large amounts of data and you encode both the dynamics as well as the appearance of your scene in these models. So of course there's like Sora. We have some work at Waabi called Copilot 4D that generates LiDAR point clouds with pretty high quality. And the recent work, I think this month, I think called Vista, which has some pretty high quality, longer duration videos for camera simulation. And I talked a bit about this earlier in the tutorial. There's like a bit of pros and cons between sensor simulation that's kind of game engine or like assets and 3D world modeling that with explicit physics, and these world models that try to implicitly model the dynamics of the scene. You have less controllability with these type of approaches, but the world models are able to generate currently a bit better extrapolation. They have better object completion, for example, compared to the scene reconstruction approaches. But there's still a lot of challenges with using these type of world models, like I talked about before, for closed loop evaluation. Cool. And then I talked primarily about sensor simulation from the rendering standpoint, but there are a couple of cool works that happened this year that are also on doing not just the sensor simulation aspect, but also having a data-driven way of generating the scene. So there's ChatSim, which is given some text prompt. It will use like GPT to kind of ask different modules to build the scene for you. So there is a module that focuses on scene reconstruction, another module that focuses on like actor placement, and it coordinates between all of these to create a particular scenario with reasonably high quality. So this might be a good way of blending both generative models with standard like physics-based rendering with explicit representations for higher fidelity. And then there's a recent OASIM simulation framework that kind of leverages neural rendering into a game engine format for higher quality sensor simulation with scenario evaluation in the loop. And lastly, I'll just talk about how with high quality sensor simulation, you can typically do end-to-end evaluation of your autonomy system on new counterfactual scenarios. So you can see like new conditions that you may not encounter in the past and see how it performs on them. All right. So in summary, we talked about different sensor simulation systems and how they all leverage some version of physics, data, and machine learning. And we list here like some of the pros of each of these types of approaches, as well as the disadvantages of using them. And you have to find the best trade-off when you combine them, particularly for your particular use case. Right. And then the last section of this tutorial session, I'll be talking about vehicle platform modeling. So this includes the dynamics of the self-driving vehicle, as well as hardware in the loop simulation. So now I'll talk about the SDV dynamics. So we just recall quickly that we have an autonomy system. It will output actuations given the sensor data of the scene. This includes, say, steering and acceleration. But then you need to actually have a model that says, given this and the SDV's position currently, what is the new position and state of the SDV? And oftentimes we have like a module in the autonomy system called a controller that tries to achieve a desired trajectory. But the real world is noisy and there's complicated physics involved. You may not necessarily be getting to the correct position that you want. So the vehicle model dynamics needs to model this like actuation outputs where the state of the SDV should be afterwards. And for like say self-driving trucks, for instance, there's not just steering angle and brake, but there's also different types of braking you can do, such as engine brake versus the throttle like pressure brakes. And these then can determine the final state of the self-driving truck. All right. So to be able to test our autonomy system end-to-end in closed loop, we need to be able to take those control actuation commands and put them into updating the state of the self-driving vehicle. And I'll briefly talk about some of the dynamics models available that are typically used to model the motion of the actor. And these are pretty simple models, but of course, there are higher fidelity vehicle models available. This is just kind of to give an overview quickly of the field. So here's an example of like a kinematic bicycle model. This model assumes you basically can convert the two front wheels with a single wheel, the two back wheels with another single wheel. And then given these two wheels, you can just assume some very standard kinematic motion of how the vehicle should move given the steering and acceleration. This kind of assumes that you have like a four-wheeled vehicle, like a sedan, but there's also extensions to these type of models to tractor trailer and larger, more complicated vehicle setups. And yeah, these are very simple, easy models, and they don't fully account for all the things you might think need to be modeled for vehicle dynamics. For example, there might be tire slip. If you have environmental conditions like wet roads, there are more changes in friction that you need to account for your vehicle dynamics that don't typically get modeled in a kinematics model. So then other model that's available is a dynamic bicycle model. This takes into account these more detailed physical parameters such as mass, moment of inertia, the weight distribution you might have on your vehicle. And it can also potentially, with higher fidelity dynamics models, take into account, say, a wet road or a very windy day to account for these more challenging situations that result in more like harder to model physics that we need to be able to do so in safety critical situations. Cool. Yeah, and I talked about earlier that we can extend these type of kinematic and dynamic models to multi-body vehicles, such as a tractor trailer setup for a self-driving truck. And yeah, there's a lot of work out there that covers this in more detail, but just wanted to briefly talk about how we have vehicle dynamics that are very key to simulate to update the state of your self-driving vehicle. And the fidelity you do it at is pretty important, especially for the self-driving vehicle. You might choose a bit higher or lower level fidelity for the other actors in your scene. All right. And then the last slide I'll talk about is hardware in the loop simulation. I talked about earlier how you have latency modeling that needs to be done if you're using software in the loop, because you need to model how long it takes for the autonomous system to run on your sensor data. But there's also ways you can build the exact hardware compute that runs on your actual self-driving vehicle as a test bench, is what it's called. These test benches are very identical to the hardware that runs on the actual self-driving truck, but instead you have it now available in the cloud to run your evaluations. And these can provide you more accurate timings of how long it takes to run different modules of your autonomy system, for example. So hardware in the loop is a bit more expensive to build these test benches, but it provides you a bit more realistic indication of your full system performance. And you can actually get true real-time measurement of how your autonomy system performs compared to the simulated version with latency in the loop. The downside is that because it's with a test bench, it's expensive, and also you cannot run faster than real time because it is running as if it was actually on the truck. So if you have much more faster or scalable simulation systems, you can run them at much faster frame rates and then run much more scenarios at scale and get better signal out on an aggregate of your scenario evaluation system. Cool. I think I went a little bit quickly, but that's the main gist of like simulation system, where we talked about primarily asset creation and sensor sim, as well as vehicle dynamics and hardware in the loop and vehicle platform modeling. I think that's it. And the next session will be from Kelvin on scene content creation and modeling the actors' dynamics. And yeah, if there's any questions, I'll be happy to answer them. I went kind of quickly for this one. Thanks. Neural rendering and reconstruction are often presented with minor changes to the original point of view from the captured scene. How do they perform with substantial changes? For example, the data captured during driving straight, and then the planner now makes a U-turn. This is a great point. So if you run, like, say, neural scene reconstruction on the original log, you assume in your reactive log replay setting that the STV does not deviate too far from its original trajectory. If you do have it deviate far, you have a significant drop in realism. And this is where you need to be able to do not just reconstruction, but also maybe scene completion or generalizability of being able to see parts of the scene that you maybe not have observed originally. Or you could potentially consider collecting much higher quality data by driving in a lot of different scenes and combining that data to create a more dense reconstruction for handling the extrapolation case. But in the current setting that a lot of the neural rendering approaches take, where you build your digital twin from a single log, you can have extrapolation artifacts when you deviate far from the original trajectory. So it's a good question. Thank you.